Hello, this is Dr. Gardner. Today we're going to be talking about temperature conversions between the Fahrenheit scale, the Celsius scale, and the Kelvin scale. Now, first of all, we're going to introduce Fahrenheit. Now, Gabriel Fahrenheit was a German-Dutch scientist that lived during the 1700s that was well known for his ability to produce alcohol and mercury thermometers. He was able to produce these types of instruments for measuring temperature, and so the Fahrenheit scale that he developed ended up being used by scientists of the time period and is still used to this day. So you can kind of imagine the reason the Fahrenheit scale ended up becoming so popular is, well, if you were looking for a way to measure temperatures in your experiments, well, you'd have to find somebody who can manufacture a device to measure those temperatures, and Gabriel Fahrenheit was the person to go to. And because the scientists of the time period used the Fahrenheit scale, we continued using it up until the modern era. However, we will also look at how the Celsius scale can have quite a few advantages and why we use the Celsius scale in the sciences as well as in our laboratories for this chemistry course. We'll also be seeing some of the advantages to using the Kelvin scale, and we're going to practice converting from one unit of measurement to the others with respect to temperatures. Now, first of all, as we look at some of our conversions today, it's maybe useful to know a few common types of temperatures on every scale. Now, if we look at the Fahrenheit scale, well, the melting point of ice is 32 degrees Fahrenheit, and the boiling point of water is 212 degrees Fahrenheit, and room temperature is roughly 77 degrees Fahrenheit, give or take a little bit, depending on what you consider a comfortable room. If we start looking at these different temperatures on the Fahrenheit scale, we can see that we have 180 divisions with respect to the melting point of ice to the boiling point of water. Now, that's a different number of divisions than we'll see on the Celsius scale in a minute. So unfortunately, the size of a degree on the Fahrenheit scale is different in size compared to that of a degree on the Celsius scale. Okay, it's actually going to be a little bit smaller, a little bit finer. You could argue that one of the reasons why the Fahrenheit scale can still be somewhat useful is that, well, the degree increments are just a little bit smaller, so the scale, it has a little bit more accuracy with, it has a little more precision with respect to the increment sizes. Okay, so that's something you should realize. Now, you might wonder why Fahrenheit picked these temperatures. Well, apparently Gabriel Fahrenheit didn't like to work with temperatures below zero. So he went ahead and made a solution of salt in ice water, which resulted in lowering the freezing point depression of the ice water to quite a bit below the temperatures he thought most researchers would be working with in the time period, and especially what he might be working with in his laboratory. And so that lowest temperature of that salt in the ice water solution he defined as the 0 point. Okay, if we look at the melting point of just standard ice water without all the salt added, we ended up with that being 32 degrees Fahrenheit. And if we think about where he might have defined roughly 100 degrees, well, up near 100, he thought about body temperature being about 96 degrees Celsius. So let's think about this. If we took divisions of 32, so I have 32 for the melting point of ice, if we consider that we could have a division of 64, which didn't have really a comparison temperature to look at, but then if we had a temperature of 96, well, Gabriel Fahrenheit thought that was body temperature. He was actually off by a few degrees, wasn't he? Okay, but if you look at those divisions, 32, 64, 96, he thought that was a very nice scale to base his divisions on. So we really didn't choose the scale with respect to the boiling point of water, but it ends up with the same size of divisions being 212 degrees Fahrenheit. Now, however, if we look at the Celsius scale you can imagine may have picked 0 degrees Celsius for the freezing point of water and 100 degrees Celsius for the boiling point of water at around sea level at an atmospheric pressure of 1 atmosphere, as having 100 divisions, just to be very consistent with the 100 divisions there. And perhaps we picked water as the compound to make these studies for freezing and boiling points because there's so much water on planet Earth. Okay, but it's going to be very handy in a chemistry laboratory where we're dealing with ice frequently in the laboratory, as well as heating up water-based solutions until they boil. So this is a very nice range for us to study. So in the chemistry laboratory, we'll use Celsius quite a bit. Now, we talk about Fahrenheit in degrees Fahrenheit and Celsius in degrees Celsius, but when we work with the Kelvin scale, we won't use the term degree. So actually, you'd be considered to use incorrect terminology if you try to use degree. So we just call them kelvins. There's no degree in the name, and in fact, other scientists would likely think that you're not very familiar with the scale if you tried to use degree when you were defining it. So it's actually your divisions in Kelvin. Now the Kelvin scale, if we look at this, the freezing point of water is at about 273, or if we wanted to go to two more decimal places, we could say 273.15. I would like you to memorize 273 first, and then try to memorize the extra digits of 273.15. Now, if we look at room temperature, well, on the Celsius scale, that was about 25 degrees Celsius. Fahrenheit was about 77 degrees Fahrenheit. And my Kelvin scale is about 298 Kelvin. So let's look at the increments in the scale and how we can relate Celsius to Kelvin. Now, the size of a Kelvin increment and a Celsius degree increment is actually the same size. So that's going to be helpful. We can see there's still 100 degrees between the freezing point of water and the boiling point of water at 1 atmosphere, and there's 100 Kelvin between the freezing point of water and the boiling point of water. It's going from 273 Kelvin to 373 Kelvin. Now you might ask, why should we use the Kelvin scale at all? Well, the Kelvin scale can be very useful in some types of calculations in science, including looking at thermodynamics calculations. When we start looking at thermodynamics calculations, well, the Kelvin scale can relate a lot to the disorder and entropy in the substances that you're looking at as we end up heating substances and going through phase changes. So it'll be very useful in keeping track of enthalpy, entropy, and Gibbs free energy to predict whether reactions are spontaneous. Okay, so it's really useful in some more advanced courses especially. You can kind of imagine maybe if molecules or atoms or ions were actually to pick their own temperature scale, perhaps they would look at Kelvin, because your temperature in Kelvin is fairly closely related to what's going on with the motion of the molecules at different temperatures. In fact, if we go to 0 degrees Celsius, we still have motion related to atoms or molecules, even if it's vibrations. And as you lower your temperature down, approaching 0 Kelvin, you end up getting less and less motion to your sample, and we've been able to achieve very low temperatures that are close to 0 Kelvin, but we haven't achieved exact 0 Kelvin by using various laboratory techniques. Okay, so the Kelvin scale we'll use frequently. We'll be using the Kelvin scale in some types of calculations, but Celsius will be the common scale that we'll use in the laboratory. But I want to be able to convert between all of these scales, Fahrenheit, Celsius, and Kelvin. Now, if I consider the very lowest temperature that we can measure, which we'll call absolute zero, on the Kelvin scale, absolute zero is at 0. If we compare 0 on the Kelvin scale, I can convert from Kelvin to Celsius by subtracting 273, or if I remember the extra digits, I can subtract 273.15 to get negative 273. Okay, if I were to convert my Celsius to Fahrenheit, we'd find absolute zero is at negative 452 degrees Fahrenheit. So these can be very useful to remember some of these common temperature relationships. I would start with the boiling point of water in all three scales and learn that, and then the room temperature roughly at 77 degrees Fahrenheit, 25 degrees Celsius, and 298 Kelvin, and learn that the freezing point of water is 32 degrees Fahrenheit, 0 Celsius, and 273 Kelvin. Those would be useful to learn first, and then if you want to give yourself an extra challenge, memorize that absolute zero at 0 Kelvin is negative 273 Kelvin, negative 273 degrees Celsius, or negative 452 degrees Fahrenheit. Okay, so that would be very useful to have some different concepts about the scale and common temperatures you might have to deal with. Okay, now let's see how we could convert between Celsius and Kelvin. Now, first of all, let's consider that if the divisions between the freezing point of water and the boiling point of water on the Fahrenheit scale are 180 divisions, and if I have 100 divisions between my freezing point of water and my boiling point of water, we can go ahead and compare this relationship. If I compare this relationship, let's write it out. So I'm going to take 180 divided by 100, and let's take a look at what that would give us. So if I have 180 divisions, whoops, just a second. If I have 180 divisions on the Fahrenheit scale, and I compare that to the number of divisions that I have on the Celsius scale at 100 divisions, Well, we could simplify this fraction down. Let's simplify this fraction of 180 to 100. That would be the same as saying that I had 9/5. Okay. So I could have 9/5, or I could recognize that 180 divided by 100 would also be equal to 1.8. So in our calculations, we'll use this relationship, either 9/5 or 1.8, for my relationship with the different sizes of divisions on the Fahrenheit degree scale and my Celsius degree scale. So let's look at the equation we could develop with this. If I recognize that if I take my degrees Fahrenheit and subtract 32 and divide by my difference in the divisions of these scales of 1.8, that would give me my temperature in degrees Celsius. So you should memorize this equation to use on the first exam. You'll have to do conversions between Celsius and Fahrenheit. Okay, so really easy to remember that equation because of the relationship of 180 degrees Fahrenheit between freezing point and boiling point of water, and the 100 degrees Celsius between freezing point and boiling point of water. Okay, so just remember the differences in freezing point. There's a difference of 32 with respect to the degrees Fahrenheit and the degrees Celsius. That's why I'm subtracting 32 here, but I also corrected for the difference in the two scales that we were looking at. Okay, so that's something to remember. Now, let's check to see if we've written this equation correctly. So if you wanted to, you can remember two of the temperatures that I asked you to learn and convert one of those to the other. So I could take one of the temperatures in degrees Fahrenheit, convert it to Celsius, and if it's the two temperatures that I memorized, I know I've written down the equation correctly. Okay, so let's go ahead and consider that. If I remember that the boiling point for water is, sorry, it should be 212 on the Fahrenheit scale, not 221. If I remember my boiling point for water, though, we can use this equation to make sure that we can convert to the correct boiling point in Celsius of 100 degrees Celsius. Okay, so if I put in 212, please excuse this typo, we would go ahead and be able to subtract 32 from it and divide by 1.8. Okay, and then what I'm going to get then is 180. You notice I did correct for that typo here. Divided by 1.8, that gives me 100 degrees Celsius. So I was able to determine my temperature in degrees Celsius. Okay. Now, let's say I want to convert 25 degrees Celsius to Fahrenheit. So I could go ahead and use the same equation, but I'm going to plug in my temperature of 25 degrees Celsius for my variable degrees Celsius right here. That's going to be equal to my degrees Fahrenheit minus 32 divided by 1.8. So I went ahead and plugged in 25 degrees Celsius. Since I had the variable of degrees Fahrenheit that I need to isolate here and solve for, I just worked with this and did a little bit of algebra. So I multiplied both sides by 1.8. Okay, and then I added 32 to both sides. So we end up with the degrees Fahrenheit being equal to 1.8 times 25 degrees Celsius plus 32. Okay, and so I end up with a temperature in degrees Fahrenheit of 77. Okay, so just remember, if you remember two of these temperatures from our table, room temperature is roughly 25 degrees Celsius, which is about 77 degrees Fahrenheit. So I could have double checked that I had set up my calculations correctly with those as a reference. So I recommend you be able to do that on a test so you can generate your equations for temperature conversions, or make sure you double check your algebra for your temperature conversions. So let's try a few calculations with temperature conversions now together. Now I'd recommend maybe pausing the video and trying to perform this temperature conversion and then seeing if you get the same answer as I give you. Okay, so pause it if you'd like, but here's the solution. If we convert 273 Kelvin to Celsius, well, I can remember that there's a difference on these two scales of about 273. In fact, if we want to remember the extra digits, it's 273.15 Kelvin. So if we write 273 Kelvin, to convert to the Celsius scale, since the Kelvin scale it has larger values, we can subtract 273 from any value on the Kelvin scale that we want to convert to Celsius, and that would give us our temperature in degrees Celsius. So this would merely be 0 degrees Celsius. Okay, or if I remember my extra decimal places, which I challenge you to try to do, I could subtract 273.15 from any temperature in Kelvin to convert to degrees Celsius. Okay, so I can do that to make those types of conversions. Now, sometimes they won't have a temperature of Kelvin exactly 273. So let's consider that we have maybe a temperature of 298 Kelvin. We want to convert that to Celsius. So I do the same type of calculation. I take 298, and any temperature in Kelvin, if I subtract 273 or 273.15, I'll get a temperature in Celsius. So that would give me a temperature here of 25 degrees Celsius. Okay. Now, so that was pretty simple. Let's try a couple of other temperatures. Let's try, and I want you to see here that 25 degrees Celsius, that's about room temperature. Remember I said 25 degrees Celsius is 298 Kelvin, so it's kind of good to kind of remember rough temperatures in each of the three scales for what the room might be. Now, of course, your lab room might vary by a couple of degrees or a couple of kelvins, and so it might range from around 20 to 28 degrees Celsius, roughly, depending on the day and whether you have a warm or cool room. Okay. Now, let's say that we have a room that is somewhat warm. So we have a temperature. If I measure that warm temperature in Kelvin, I might measure that it's 300 Kelvin to 3 significant figures. So if I want to convert that to Celsius, I merely take the 300 Kelvin and subtract 273. I put the decimal point to indicate that I did have 3 significant figures. I subtract 273 Kelvin from the Kelvin value. We end up getting an answer here of, in this case, 27 degrees Celsius. Okay, that would be my temperature in Celsius. Now, however, I want to convert all the way to Fahrenheit. So we had an easy conversion between Kelvin to Celsius, so I did that first. Okay, and once I'm in Celsius, well, we had an equation for being able to convert from Celsius to Fahrenheit or Fahrenheit to Celsius. Now, the equation that I said you maybe should learn is that degrees Celsius are equal to my degrees Fahrenheit. Now, I'm thinking it's minus 32 because the difference in the freezing points on the two scale are 32 degrees. But the divisions between the two scales aren't the same. Remember, there's 180 divisions on the Fahrenheit scale and 100 divisions on the Celsius scale. So I'm going to divide by that relationship. I could divide by 9/5, or I could think I'm taking 180 divided by 100. That's 1.8. So I'm dividing by 9/5, or 1.8. Okay, so I'm going to find then my temperature here. Well, in fact, I can't solve it just as is because I had a temperature in Celsius and I need to solve for Fahrenheit. So I rearrange algebraically to solve for Fahrenheit. So my degrees Fahrenheit I would find once I rearrange this equation to isolate that variable. Now I'm doing this by multiplying both sides by 1.8, right, and adding 32 to both sides. Okay, so I end up with degrees Fahrenheit being equal to my degrees Celsius. My degrees Celsius here. Sorry, let's write it over here. Degrees Celsius times 1.8. Okay, and then I add 32. Okay, so if you've calculated this correctly, we'd find that our temperature would be 81 degrees Fahrenheit. Okay. Now I should be able to, on a test, be able to convert from Kelvin to Celsius or Kelvin to Fahrenheit. I should also be able to convert from Fahrenheit back to Celsius using this equation here. And I should be able to convert Celsius back to Kelvin by adding 273. So I should be able to work these types of problems both directions. Okay. Now the next calculation I'd like you to look at is determining if you're sitting in a room at 68 degrees Fahrenheit, so we're a little cool in this room, right? Let's convert that temperature in Fahrenheit to Celsius and to Kelvin. So I recommend that you pause this video, try performing the calculation, and see if you find the answer here. Okay, so go ahead and pause that video and give it a try. Okay, so now that you've tried to answer this question, let's go ahead and determine what your answers would be. Okay, so here we would have for the first part of the calculation, I'm going to convert from my degrees Fahrenheit to Celsius. So I'm remembering, in this case, that I have degrees Celsius is equal to my degrees Fahrenheit. My difference in the freezing point of water for both scales is 32, so I'm subtracting 32. And then the difference in size of the two scales, well, there's 180 divisions between freezing point and boiling point of water for Fahrenheit and 100 divisions for Celsius. So I end up with 180 divided by 100, or 9/5. So I put 1.8 or 9/5 in the denominator and dividing by 1.8. Okay. Now, what I would find then when I plug in my temperature of 68 Fahrenheit and subtract 32 divided by 1.8, we'd find that we have a temperature in this case of 20 degrees Celsius. Okay, so now if you want to determine why I kept this number of significant figures, we can remember though that the 68.0 degrees Fahrenheit had 3 significant figures. When I subtracted 32, we counted the difference between the boiling point and melting point on the two scales. So I'm treating that as an exact or defined number here. Plus our divisions of 100 divisions on the Celsius scale are 180 on the Fahrenheit scale between freezing point and boiling point of water. Those are counted numbers of divisions. So I'm also treating these as exact numbers or defined numbers with infinite significant figures. So I was limiting my significant figures by the temperature in Fahrenheit. So I get 20.0 degrees Celsius to 3 significant figures for my answer. Now that's one part of my answer here. I also wanted to calculate my kelvins. So if I want to calculate my kelvins, well, we know that we can just take the 20 degrees Celsius, okay, and we can add 273 or 273.15 once you learn the extra decimal places to determine my temperatures in Kelvin. Let's say that we remembered the conversion here to some extra decimal places. So I took 20.0 degrees Celsius and I'm going to add 273.15. Okay, I'd end up with an answer of 293.15, which I'm going to round here. If I look at it, I have the tenths place as my last significant figure during the addition process here, right? So I'm not just counting the number of significant digits. For addition or subtraction, we're looking at the last significant digit with respect to being in the tenths place, so I had to round to the tenths place for the answer, so I end up with 293.2 Kelvin. Okay, so we've practiced several calculations here today with conversions between Celsius and Kelvin. As I said, on this next exam, you should need to be able to convert between Kelvin and Celsius, or Celsius to Kelvin, or from Kelvin to Fahrenheit, or Fahrenheit to Kelvin, or between Celsius and Fahrenheit and Celsius. You should be able to make any of those conversions on that exam. I'll pick several of them to have you perform. Okay. Well, thank you very much. Before exam 1, there will be some extra problems that you should be working in the classroom to help you practice. So I'll be emailing that out to all of you. Thank you.